Okay. So here we are given 8 Qpsk signal. Okay. We are given 8 Qpsk signal. 8 Qpsk signal. Okay. That means we will have we will we will have 8 symbol. Okay, we will have 8 symbol. That means 8 waveform. Okay, that means 8 waveform, and each waveform has same amplitude, and same frequency, but different phases. So we will be having 8 phases. Okay, we will be having 8 phases. Okay, so this one has 0 phase. This one has some phase. Okay, strictly speaking, this will be have 5/4 phase, and this symbol will have 5/2 phase. Likewise, you can calculate the phase using the consolation diagram. Okay. The other point is, since we have same amplitude, okay, same amplitude, all these symbols has same energy. So let's say that it is ES. So this is the symbol energy. Okay, so all this will have same energy, and if you find the average symbol energy, that also will be equal to ES, because we have to multiply 8ES by and divided it by 8. Then also you will get ES, that is the average symbol energy. Okay, so the average symbol energy and symbol energy are same in PSK. Okay, we have already seen this, but it not in same in QCAN or ASK modulation scheme. Okay, so this is ES. Now we are asked to draw and explain the decision region. Very easy. Okay, so you can draw the decision region. Okay, like this. So okay, so this will be your decision region. This is one region. Okay, this will be one region. So these are the decision region, decision boundaries. Actually, these are decision boundaries. Okay, so decision region will be this. Okay, these are the decision regions. I think if you draw the decision boundary, it is enough. Okay, if you draw the decision boundaries, it is enough, because using the boundaries we can verify what are the decision regions. Okay, if you have drawn the boundaries, it also define the regions also. So you can see that for S2 this will be the decision region. Okay, so any received bit is between here in this region, it will be decoded as S2. If any received bit is, for example, in this region, okay, it will decoded as S1. Okay, so that is the decision region. So you can go it. Okay, the condition is, okay, when you are finding the decision region between these two adjacent points, you have to get the same length. Okay, so this the half length. Okay, so from decision boundaries, this length and this length should be same. If you consider this one, this two, okay, and the decision boundary will be look like, and this one will be same. So you will be having this kind of different decision region for S2. Okay, so that is the way to draw the decision boundaries or decision regions. Okay, so I hope you can do this. Then calculate the average symbol energy and average bit energy in terms of X. So what is X? So this is the X. Okay, so what is the symbol energy? What is the symbol energy? Yes, what is the symbol energy? Very simple. Is Someone feedback if you are there. So what is the symbol energy? So you can see that this x is the distance from here to here. So what is this refer? This is the amplitude. This is the amplitude. So x is the amplitude of the signal. Okay, amplitude of the waveform. Then what is the energy? Very simple. What will be the energy? Yes, it is x square. Okay, so the symbol energy will be one symbol energy will be x square. Okay, so that is very easy. Okay, and so here they are asking average symbol energy, not a symbol energy, average symbol energy. Okay, you can see that every symbol has the same energy, that is x square. So if you find the average symbol energy, average, okay, what you have to do? You have to divide, you have to multiply it by all the symbol and divide that by 8. Okay, so you will get again yes. Okay, so average energy symbol also equal to energy symbol. Uh, energy of the symbol, energy of a symbol energy. Okay, so your average symbol energy and symbol energy will be equal, and it is equal to x square. Okay, so that is that average symbol energy, that is equal to es, and that is equal to x square. So what is the average bit energy? So what is the bit energy? So how many bits with this symbol? So this is 8 Qpsk. So how many bits here? And someone feedback? There should be 3 bits. Okay. So so this is the power of 3 bits. Es symbol energy. Okay. So that means it is the energy of 3 bits. Okay. To find the 1 bit energy, what you have to do? You have to divide this by 3. Okay. So this will be your average bit energy. Okay. So here you have in one symbol, you have 3 bits. Okay. So that is that. Okay. Now propose the gray coding scheme clearly showing the allocated signal. So you can simply do it. Okay. So actually here I have a note. Okay. I have a diagram. So I, I write it by looking at the diagram. Okay. But you can do this by your mind. You no need to do any hard work. Okay. So you can assign any value here. I use 0, 0, 1. Now you have to uh, you have to you have to uh, change one bit in every symbol. Okay, only one bit. Okay, but when you are doing the doing this last time, you have to be somewhat careful, because sometime if you change one bit here, with this you will have 2 bits difference. Okay, so you have to be careful to avoid it. Okay, so that is the requirement. Anyway, this is not much difficult. Okay, so I can write here 101, only one, sorry, 100, no? Okay, only one change, only one bit is change. Here you can put 110. Okay, here you can put 010. Here you can put 00011. Here you can put 111. Here you can put what is that? You can put 101. 101, no? You can put it because only one change, 101. Here you can put 111. He is here. 101. What is the missing one? 00, 100, 110, 011, 001. No? Okay. So you can put 001 here. Only one bit change. Okay. Here also only one bit. Okay. So you can see that only one bit is changing. Okay. So likewise, you can propose a gray coding scheme. Okay. And what is the special feature here? The two adjacent bit, between two adjacent symbol, there should be one bit change. There should be one bit position change. Okay, only one bit change. That is the special feature. Okay. Now we come to the important point. Now you have to compare the two modulation schemes. Okay. So now you have to consider. Okay. So we are going to compare 8PSK and QPSK system. Okay. So 8PSK, and so now we have 8PSK. Now we have found some parameters related with the 8PSK scheme. Okay. Now we are asked to design a QPSK system. Okay. Now let's move. Okay. Now you know that in QPSK, okay, in QPSK, you will be having uh, four symbol. Okay, four symbol. You will be having two basic function and four symbol. Let's mark the four symbols are like this. Okay, so these are the four symbols. Let's say that this is S1, S2, S3, S4. So these are the four symbols. Okay. now, okay. Now, if the same energy per bits value is to be maintained for both system, okay. So here the bit, okay. So you have to careful with these terms, okay. Sometime it asks to change, it asks to keep the same symbol energy, okay. But here it is asked to maintain same bit energy, okay. So if you have understand this, it is not much difficult. Okay, don't try to do with if you do this with the understanding, that will not give you any wrong answer. Okay, so you can see that now the same energy per bits. Okay, so we have calculate the energy per bits, that is x square by 3. So this is our bit energy. Okay, so if I am doing any mistake, you can ask me. Okay, okay, so this should be our bit energy, x square by 3. Okay, so this will be our bit energy. Okay, and we have to have the same energy in this bits also. Okay, so you know that this is 4 QPSK, 4 PSK. That is, we call instead of this 4, we called it QPSK, quadrature phase shift key. Okay, so here you have 4 symbol, 1, 2, 3, 4. That means in each symbol you have 2 bits. Okay, so maybe 2 bits. Here also you can use the gray coding. Okay, so this should be 0, 0, 0. Okay, this should be 0, 1. This can be 1, 1. Okay, so this also gray coding. No? This also gray coding. Okay, so I just write this. Okay, it is not asked to write. Okay, but I just write this. Okay, okay, likewise. So you can see that you have 2 bits. per one symbol. You have 2 bits per one symbol. Now, you also can see that this distance, this distance, this distance are same. Okay, so tell me in Qpsk, all symbols have same energy or not? All symbols have same energy or not? Energy or not? Tell me. Yes, same energy. We have same energy because these symbols are located in a circle with radius, some radius. Okay, so this will be the radius. Okay, so these all symbols have one energy. Okay, so let's say that the symbol energy is ES1. Okay, so the symbol energy is ES1. Okay, so symbol energy is ES1. I just take. Okay, so energy, symbol energy is ES1. Okay, so then what is the bit energy? What is the bit energy? Bit energy is, so one symbol has 2 bits. One symbol has 2 bits. Okay, I think the students are so if you try to copy in the end examination, you know that the Tilanka madam is very strict. Okay, in case of copying. Okay, so actually I think that is why she gave the things like this. Okay, by changing. Okay, so if you at once, if you think that this is the energy symbol, the energy of a symbol, this is a symbol energy, so you will so if you copy, you will have the same mistake. So she can verify that you have copied very quickly. Okay, so be careful. Okay, with this kind of tricks. Okay, so if you can do this by yourself, that is no problem. Okay. Okay, and also once you have done this by yourself, please don't send the answers to others. Okay, it will be monitored, and you will get some lower marks. Okay, you will uh, you will get reduce some marks. Okay. Okay, so we will move. Okay, so so we have, so this is a symbol energy. Okay, and we have one symbol, we have 2 bits. Okay, so bit energy, let's say that it is B1. Okay, EB1, this is Qpsk. Okay, so this is for Qpsk, EB1. Okay, so it should be ES1 divided by 2. So this will be the bit energy. Okay, now this bit energy, ES1 divided by 2, should be equal to the average bit energy here. Okay, so I equal it to here, x square by 2, correct? S square by 3, correct? Okay, so what is ES1? What is the symbol energy, average symbol energy? It will be 2x square by 3. That will be 2x square by 3. So that is the symbol energy. Symbol energy. That is a symbol energy. Energy per symbol. Okay. This. Okay. So how you calculate it? You just equal the average bit energies. Okay. So this is the average bit energy for Qpsk. And this is the average bit energy for 8psk. Okay, you have equally because it is said to equal. Okay, it is said to equal. Okay, okay, I hope you get. Okay, so that is the symbol energy. Okay, that is the symbol energy, and of course you can find the bit energy also. Bit energy will be this one, same, and also if you divided symbol energy by 2, you will get the same value. So it will be x square by 3. Okay, so this is for Qpsk. This is for Qpsk symbol energy, and this is Qpsk bit energy. Okay, this is Qpsk bit energy. Okay, Okay, we have verified it. Now find the radius to be maintained for the cube. Okay, now we have to find the radius. Okay, so you can see that this radius is directly related with the symbol energy. Okay, actually, if the radius is r, what is the symbol energy? What is the symbol energy? That is r square. No, if the uh, radius is r, r square is the symbol energy. Symbol energy of the Qpsk system, ES1. That is equal to 2x square by 3. Then you can get r is equal to, so you can get the square root, then 2, 3x. Okay, so this will be the radius. This will be the radius of Qpsk circle. This is the radius of Qpsk circle. Okay, so we have found it. Okay, now we have found this. Now critically evaluate and explain the difference in probabilities of error of these 8PSK and QPSK scheme based on the minimum distance between the symbol. Okay, now you have to calculate the minimum distance. Okay, so very easily you can calculate it. If you consider these two symbols, okay, so this will be 5 by 4, okay, 5 by 4. And if you again get this kind of line, this will be 5 by 8, and also this will be 5 by 8. Okay, and this will be the radius or the energy of the symbol. Okay, the root energy of the symbol. Okay, so it will be root energy of the symbol sine 5 by 8. Actually this 8 is m. Okay, this 8 means m. We have seen this. Okay, and we have to that is this one, and this one is also root t sine 5 by m. Okay, so you have to add to find this value, so it will be 2 root ts sine 5 by 2. So this is d mean. Okay, so now you can find the d mean for both case. Okay, d mean for both case. Okay, so let's say that d mean for Qpsk, what is that? That is 2 root ES1. Okay, that is the symbol energy of Qpsk, ES1, this one. Okay, ES1 sine 5 by m. M is 4, sine 5 by 4. And what is the D mean for 8PSK? That is 2 root ES. Okay, that is root ES. We get it as ES, no? Yeah, ES. That is sine 5 by 8. Okay, so what is the value here and what is the value here? So you know that 2 root ES is 2 root ES means this one, no? X 2, 3. Okay, so this is root ES. Okay, we have found this one. 2 by root 3 sine by 5 by 4. What is sine by 5 by 4? What is the value? And can someone tell me? What is the value here? Okay, 1 by square root 2. Okay, 1 by square root 2. Okay, so you will have this distance for Qpsk. And what is the value for 8PSK? You will have, so you will have 2 here, the 2 we forgot, no? We have 2 here. Okay. And here also you have 2. Now root ES. ES is x, no? Root ES is x. ES is x square. So root 2 ES means that is x. So you have x. What is the sine 5 by 8 value? What is the value for sine 5 by 8? Can anyone tell me? What is the sign 5 by 8? You can tell me in just use the calculator and decimal value. Tell me the decimal value. I think point, you will get some point value, 0 point value. Tell me that value. Can someone tell me, please? I will have different values, two different values. So I think two student has sent same value. So I will take this, take that one. That is 0.38. Okay. It is given the paper, no? Okay. Okay. That is 0.38. Is that okay? 0.38. Okay. Okay. Now, now you can see that this root and this root will cancel out. Okay. 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 So, so what is the value for this? So you can see that this one and this one cancelled out. So you have to get 1 by root 3. So please use a calculator and tell me this value. What is this value? 2 by root 3. That is 0.058x. And what is the value for this? What is the value for this? It should be 1.154. Sure. Okay, let's say 0.768. Sure, no? Okay, so now you can see that. Okay, now you can see that. Okay, actually you can get a good point here. Okay, now you can get that this point, this 2 point, this 2 point. Okay. So in Qpsk, so 16 psk, 16 psk, your distance is high. Okay, so this distance is high and this distance will be low. Okay, so you can see that this 8 psk, in this case 8 psk modulation is more efficient. It has lower error probability, because the length is somewhat high, and uh, 4 psk, 4 psk will have, 4 psk will have uh, higher error probability, higher error probability. Okay, so this is the conclusion, no? Based on the minimum distance. Okay, so no, but normally we are so normal procedure is, if we consider the Qpsk like this. Okay, and if you have a 8 psk like this. Okay, like this. So normally this distance, so we have many cancellation point here, consolation point here. So normally this distance will be greater than this one. Okay, this one, but it is not happen here. Why? What is the reason? So you know that normally the Qpsk is have lower probability. This has lower data rate. Okay, so this will have lower data rate, but it will have lower error probability, lower data rate and lower error probability. This will have higher data rate because here in one symbol you are sending 3 bits. Here in one symbol you are sending only 2 bits. So here we have higher data rate, okay, because you are sending 3 bits at once, okay, higher data rate. But here you have higher data error probability, also higher error probability. So this is the normal comparison. But in this case, we have different one. This system have low data rate, definitely, but higher error probability, higher error probability. No, this one has higher data rate, but lower error probability. So you can see that this is magnificent, no? This is magnificent, but this is very bad. Okay. So how can you justify this? You know that if you want to sacrifice one thing, we have to sacrifice another, no? If you want to get something, we have to sacrifice another things. Okay. Okay. So here, in order to have a lower error probability, you sacrifice the data rate to have a higher data rate. You sacrifice the error probability here. But here, okay. So what we sacrifice here actually in this case? Can anyone tell? Can anyone tell what we have sacrificed here? Why we have sacrificed here in this case? We sacrificed the bit energy, no, symbol energy actually, symbol energy. Okay, because you can see that here in this 8 PSK, you have x square symbol energy. Okay, x square symbol energy. But in PSK, in Qpsk, you have 2 by 3 x square. Okay, so in Qpsk, you have a square symbol energy. Your waveform have this energy. Okay, that means your waveform have more power. So here you have to give more power. You are given more power. You are given more signal power. Okay, but in this case, in this Qpsk, you are given less transmission power. You are given loss energy, low energy. Okay, because this is around 0.6 x square. No? Okay, so if you are given here, let's say that 20 watt for transmission, here you are given only 12 volt. No, only 12 volt. So in this case, you use very low power, very low transmission power. Your transmission signal power is very low. Okay, but here your transmission signal power is very high. So that you sacrifice here. Okay, that is why it happened like this. Okay, so here you use in 4PSK, you use very low transmission power. Transmission power. So here you can save the power. You can save the power. Okay, you can save the power. Although you have sacrificed the higher data rate and error probability, but you can save some power here. In this days, I think this is the best solution, no? because we don't have much power. Okay. Okay. I just joke. Just have a joke. Okay. So this day we have to save the power as much as possible. So we can sacrifice the data rate and the error probability, and we can save the power here. Okay, did you get this? Okay, did you get this? So if you have any problem, you can just verify it here. Okay. Okay. Now I will be moving to the next one also. Okay. So I think you clear this, no? Okay. You clear this, I hope. Okay. So if you tell the summary, okay. So you have a PSK and you have 4 PSK, okay. And here D mean is high, okay. Distance is high, so you will have low error probability. Error probability. And you can see that this distance also depend on the energy of the symbol. But here, the energy of the symbols are very high. Okay? In 4PSK, you will have D mean very low D mean. Okay, so you will have higher error probability. Higher error probability. Okay, probability. But here, the symbol power is very low. Okay, so here you have lower data rate, and here also we have higher data rate. Okay. The mean QPSK should be 1.154. You means here it should be 15154. X. Okay, then so it is okay. Okay, so I think that explanation is okay. Okay, what I explained is very clear. It is very true. Okay, because if you are using less power, if you are using less power, if you are using 4PSK, your distance can be very low. Okay, but if you are using very higher power, okay, so this is the R. Okay, this is the R for this PSK. And if you are using very higher power, okay, very higher power, okay, like this, okay, then you can see that this distance is greater than this one, definitely greater than this one. Okay, definitely. So by increasing the power of the signal, okay, by increasing the power of the signal, we can uh, reduce the error probability. We can reduce the error probability. So it is not a waste of time. Okay, if you get this idea, it is I think it is very well. It will be if you get very high power, you can reduce the error probability. But again, you will face some problem. Okay, higher power means you will get more power. Okay, so sometimes it can be damaged. The receiver, if the receiver is very near, the receiver can be damaged due to high power. Okay, so there are some what is called trade-offs are there. Okay, but anyway, if you can increase the power, you can reduce the error probability. Okay, but it can be happen. Okay, so I think that it is happen here, but I think still it is not enough. Okay, still if you are using low power here, okay, if you are using the low power here, okay, low power is still this distance is greater than the 8 QPSK distance. here your power is somewhat low. Okay, in Qpsk, your power is somewhat low. Okay, but anyway, if you are using 8psk with slight higher power, okay, but it will not much, it will be not enough to to reduce this gap, to increase this gap than this one. Okay, so here it is same. So here in so you can compare it with the same manner. Okay, if you said that the Qpsk distance is 1.15x, that means Qpsk distance is still high. Okay, distance of Qpsk is still high, so you will have low energy, low data rate, low data rate, sorry, low data rate and low error probability, okay. And the 8psk, the distance is still high, still low, okay. Although you are using slightly high power, it is still low. It is not enough to maintain to fill that gap, okay. And you will have higher error probability. Okay, higher error probability. Anyway, I think that mistake will give you a good understanding. Okay, okay. I think that is true. That is okay. Okay, we can reduce the error probability by increasing the power. Okay, okay. So I think in both way you can explain this. Okay. So are you okay with this? So do you have any doubts? Are you okay with this? So our answer is different. Okay, our answer is different. Okay, our answer is not this one, but these facts are correct. Okay, but that is what I want to. So these facts are correct, but these facts are not correct in this case. Okay, in this case also, you will have 8psk. D mean is low. Okay, so you will have higher error probability. Okay, and for psk you will have d mean high. Okay, so you will have lower error probability. So this should be your answer. Okay, but these facts are not wrong. Okay, these are correct. Okay, okay. So so if you have any problem, you can ask. So quickly I will try to do this one also. Okay, okay. So try to compare it with this one. Okay. So here, I think you have to be very careful. Okay, here again, she is asking to uh, to uh, to uh, to equal the symbol energy. Okay, not the bit energy. Okay, in this case, she is again asked to equal the symbol energy. Okay, anyway, I will do this. Okay, I will try to do this. So I will do, so I'm not going to do it with this one. Okay, I will do it with my system. Okay, now again we are asked to, okay, so you can generalize it to here. Okay, so some fact may be changed, but this will be an important discussion. Okay, so I will be doing that one. Okay. Okay, so I will take this. Okay, now we are asked to we are required to design the 8 ASK modulation. scheme. Okay, so we have to design 8ASK modulation design. 8ASK means we will have 8 symbols. Okay, we will have 8 symbols, and all symbols will have same frequency, same phase, but different amplitude. So this will be, let's say this is our first symbol S1. Okay, so this is S2, this is S3, this is S4, this is S5, this is X6, this is S7, this is S8. Okay, so I think in previous example I take this as 0. Okay, so we will have up to 7. Okay, but don't confuse. Okay, this also okay. So I start from S1. So this is symbol 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 8 symbols. What is the condition? The distance should be same. All these distance should be same. So this should be R, this should be R, this should be R, so on. So what is this distance? So you will have 0. This distance you will have R. Here you will have 2R. Here you will have 3R. This is you will have S1, S2, S3. You will have 4R. You will have 5R. Okay, you will have 5R. You will have 6R. You will have 7R. Okay, so these are the distance. Okay, so you can see that these are the these are the consolation point waveform, and all each waveform has a different amplitude. So this waveform has 0 amplitude. That means no transmission here. Okay, no transmission, not EX. Okay, and here your amplitude is R. Here twice 2R. Here it is 3 times 3R, like 1. Okay. Okay. So this is the amplitude. Okay, so if you so you can see that the symbols energy are not equal. Okay, because it has different amplitude. Okay, symbol energy has are not different. Okay, so if I calculate the symbol energy, okay, so total energy, I calculate the total energy. So total energy will be 0, because first symbol doesn't have any energy. Okay, so this one, the amplitude of this one will R. So we will have R square energy. Okay, and the amplitude of second one is 2R. So we will have 2R energy, and we will have 3R energy. We will have 4R energy, and we will have 5R plus 6R plus 7R. So someone calculate this very quickly. What is the value here? What is the value here? The total power, total energy. What is that one? So you will have R square here. You will have 0 plus 4 plus 1 plus 9 plus 16 plus 25. So what are the values? So what is the sum? What is the value here? Can just use the calculator and tell me. Yes, it is 140. No? Okay. So we have 140 R square. Thank you. So total energy will be 140 R square. Okay. So we have 8 bits. So we have to divide this by 8. So you can find the average energy. Average symbol energy for FSK, 8S FSK. Okay. So what is the value here? So you have 1. Okay. 186. Okay. So you have 17.1, no? 17.5 R. Okay, R square. So this will be your average energy of a symbol. Okay, average energy of a symbol. Okay, average symbol energy. Let's say that it is average symbol energy for FSK. That is 17.5 R square. Okay. So now we are we are we have to design this FSK. The average symbol energy, okay, for FSK should be equal to the average symbol energy of this this 8 Psk value. Okay, so this is 8 Psk. So what is the average symbol value here? X square. So this will be the symbol energy. Okay, and this symbol energy and that symbol energy should be equal. Okay, so this is the average symbol energy for Fsk, and it should be equal to the average symbol energy of Psk, 8 Psk. Okay, what is that? X square. Okay, so you can see that 14.5 r square is equal to x square. Now you can find this r value. So it will be x by root 17.5. Can someone tell me the r value in terms of x? In terms of x? It is 0.239, that is 0.24, 0.24x. Okay. So this is the R for this is the R for the minimum distance for FSK, no? Okay. So now you have to compare. Okay. So minimum distance, the mean of PSK is, what is that? That is uh, 2x sine 5 by 8. No? So what is this value? 0.766. Am I right? Is this the value? And FSK will be 0.24x. So you can see that. Okay, thank you. Okay, so I think this one is correct. Okay, okay. So you can see that the PSK is greater than, PSK distance is greater than FSK. Okay, so let's say that this is D1 and this is D2. So D1 is greater than D2. Okay, so you can say that the error probability is less than this one. Okay, error probability of 8 PSK is less than error probability of 8 FSK. So that is the that is your answer. Okay. Yeah. So 8 ASK. Okay, 8 ASK. Sorry. Oh, sorry. So this is ASK. Okay, I'm sorry. Okay, this is amplitude shifting, not frequency shifting, because for frequency shifting we need two basis function. Okay. No, two basis function. Yeah, maybe. I can't remember. Okay. So this is ASK. Okay. I'm sorry. This is amplitude shifting. Okay. So this is amplitude shifting ASK. Okay. Okay. So I think you have done. Okay. You have. I think you can do this type of question by yourself. Okay. So what you have to know, what should you need to do is you have a good idea about the consolation diagram. Okay, consolation diagram, because if you have idea about the consolation diagram, you can answer all these questions very easy. Okay? So do you have any problem, any other problem? If you doesn't have any problem, we will wind up. Okay, I will upload the recorded session.